This is section 3.7, which is pretty intense, but I'm going to try and make it as painless for you as possible. An improper integral is one where one of the limits is infinity, like this, or both the limits are just finite numbers, but the function has a discontinuity somewhere in between the two limits. So we're going to take a look at both types of those. Before we do that, I just want to go over some limits with you that you'll need. And I think just remembering these pictures, these three pictures up here, will help you a lot. So these are common limits that come up when you're doing improper integrals. The first one involves tangent inverse. So tangent inverse has two horizontal asymptotes. The top one is at pi over 2. And the bottom one is at negative pi over 2. So if you're going this way, if x is going to infinity, tangent inverse of x is going to approach pi over 2. And if you're going the other way, x goes to negative infinity, tangent inverse is going to go to negative pi over 2. All right, the next ones involve e to the x and e to the negative x. And those are pretty easy to remember. E to the x is the blue graph. You all know that. E to the negative x is just the reflection of that about the y-axis. That's the green graph. So as x goes to infinity, e to the negative x. So we're looking at the green graph. As x goes to infinity, the y values are getting closer and closer to 0. And if we go in the other direction, this way, the values go to infinity. And for e to the x, they do the opposite. As x goes to infinity, e to the x goes up forever. And as x goes to negative infinity, e to the x gets really close to the x-axis. The y values approach 0. Last one is from the graph of y equals ln x. Y equals ln x grows slowly, but it does grow. So as x goes to infinity, ln x eventually gets to infinity. And then notice here I have the limit as x goes to 0 from the right, because I can't just say the limit as x goes to 0 of ln x, because that wouldn't make any sense. There is no approach from the left, because as you can see, the graph doesn't exist on the left. So you can only approach 0 from the right, and you can see these y values are dropping down to negative infinity. Okay, so now let's talk about the first type of improper integral, which is the easy type, because it's easy to recognize because you'll see infinity in one of the limits. And so the first step is to rewrite it as the limit of a proper integral. So think of it in terms of area. If you're integrating from a to infinity, the integral of f of x dx, and here's the graph, what you really want is to know what that area is all the way out to infinity. And so the way we do that is we say, okay, I have no idea what that is, but I can just go from a to k and compute that area. That would be the green shaded area. Then, once I know that number, I'll push k to infinity. And so the idea is you replace this improper integral, you go from a to k, and then in front, you take limit as k goes to infinity, and you evaluate that. So, in terms of how to do this in steps, step 1, rewrite. And so I have an example over here. I want to go from 1 to infinity, x to the negative 2 dx. So instead of going from 1 to infinity, I go from 1 to k, and then I take the limit as k goes to infinity. Step 2, just evaluate this part. Leave the limit off and evaluate the proper integral, and there'll be a k in your answer. And so I did that, and you can see I got negative 1 over k minus 1. You can pause the video and make sure that you can do all those steps. And that's just the same as 1 minus 1 over k. And then the third step, take that limit that was on the first step and put it back on and take the limit of your answer. And in this case, as k goes to infinity, 1 over k goes to 0, so my limit is 1. And I say that the integral converges to 1. Now, if I had gotten infinity or negative infinity, I would say the integral diverges. And if one of the limits is negative infinity, you're going to do the same thing. So here's a picture of that. You want to go from negative infinity to b. So instead, you go from k to b, and then you push k to negative infinity. Let's look at an example. Find the area under the curve, y equals 1 over root x, from 4 to infinity. Let's just say here's 4, and I want to find all this area. And so remember, the formula for the area on the curve is integral of top curve minus bottom curve. In this case, the bottom curve is y equals 0 because it's the x-axis. The area is going to be the integral from 4 to infinity of top curve, which is 1 over root x, minus bottom curve, which is 0, so I'm not going to write minus 0, dx. So step 1 is rewrite this as the limit of a proper integral. So I want the limit as k goes to infinity, and I'll integrate from 4 to k. And I'm going to rewrite my integrand as x to the negative 1/2 to make the integration easier. Step 2, you can just evaluate this guy. So we're going to evaluate the proper integral. And so 2x to the 1/2 between k and 4, which is going to be 2 square root of k minus 4. All right, in step 3, we're going to put our limit back on and take the limit of that answer. The limit, so the area is going to be, if it exists, the area is going to be the limit as k goes to infinity of 2 root k minus 4. Okay, square root of k as k goes to infinity. So that's going to be infinity minus 4, which is still infinity. So we say that integral diverges. Integral diverges, so the area is infinite. Okay, let's do another one where the area is not going to be infinite. Okay, and I'm drawing us a picture. So step 1, we want to write this as the limit of a proper integral. So we're going to go limit as k goes to negative infinity, and we'll go from k to 2 over x squared plus 4 dx. Okay, step 2, we want to evaluate that integral. Leave the limit off for now. All right, and that's a tangent inverse. And so I'll have 2, this 2 up here, you can just pull out like that. But then when you integrate 1 over x squared plus 4, you'll get 1/2 tangent inverse of x over 2. So clearly these guys cancel, and our limits are 2 and k. So that's going to be tangent inverse of 2 over 2 is 1 minus tangent inverse of k over 2. Now tangent inverse of 1 is pi over 4. All right, step 3, we're going to take the limit of that. Limit k goes to negative infinity, pi over 4 minus tangent inverse of k over 2. This limit is going to be, I'm going to drop the limit sign. This is equal to pi over 4 minus negative pi over 2. So my area is actually finite. It's 3 pi over 4. So what we do is we say the integral converges to this number, and that is the area underneath that curve. All right, so now type 2 is a little more tricky, kind of insidious, because you might not even recognize it's improper. It's the same idea though. Suppose your function is a discontinuity at b, the top limit. Then what you're going to do is integrate from a to k, and then push k towards b from the left. And I always draw a picture, not necessarily of the graph, but I draw a picture of the interval so I know what direction I'm coming from. Is k coming from the left or the right? If the problem is at the lower limit, a, you're going to go from k to b, and then you'll push k to a from the right. I know, it's confusing, but you'll see it's not that bad. Here we go. We want to go from 0 to infinity, 1 over x squared dx. You might not even recognize that's an improper integral. You might just do it out and get an answer, but the problem is your answer would probably be garbage. And the reason is because 1 over x squared is not even defined at 0. So our problem is at 0. And so what I do, I'm going to draw the interval from 0 to 1. So since the problem is at 0, I'm going to put a k closer to the 0 side. I'm going to integrate from k to 1, and I'm going to push k to 0 from the right. So the first step to rewrite this, I'm going to rewrite this integral as the limit as k goes to 0 from the right of integral from k to 1, and I'm going to write 1 over x squared as x to the negative 2 so that I can integrate. And it's so helpful to draw this picture of the interval to help you with that step. Okay, so now step 2 is just to evaluate the integral. K to 1, x to the negative 2 dx. dx. That would be negative 1 over x between 1 and k. So that's negative 1 minus 1 over k, which I'll just rewrite as 1 over k minus 1. And then the last step, put that limit back on, the limit from step 1. Limit k goes to 0 from the right of 1 over k minus 1. All right, so this is a little tricky. So 1 over k is going to 0 from the right. That's going to be 1 over 0 from the right. So we're approaching 0 through positive values. And then, of course, we're subtracting 1. But 1 over 0 through positive values is infinity. So we're getting infinity minus 1, which is still infinity. So the integral diverges. Okay, so practice. Pause the video, do this one, and then come back. Okay, hopefully you did it, and hopefully you got pi over 2. All right, so let's look at this guy. There's no problem at 0, because when I put 0 in for x, I get 1 over the square root of 4, no problems there. But when I put in 2 squared is 4, I'm dividing by 0. So now the problem is at the upper limit. So I'm going to draw a picture of the interval, 0 to 2. My problem's up here at 2, so I'm going to put k close to 2. I'm going to integrate from 0 to k, and then I'm going to push k towards 2 from the left. So step 1, I want the limit as k goes to 2 from the left, and I'm going to integrate from 0 to k. And my integrand is 1 over the square root of 4 minus x squared, which I hope you all recognize as a sine inverse. So step 2, we just want to evaluate this guy. Now remember, sine inverse is the only one that doesn't have a 1 over k that comes out front. Like, so there's going to be no 1/2 that comes out front. We're just going to get sine inverse of x over 2 between our two limits, 0 and k. All right, so that's sine inverse of k over 2 minus sine inverse of 0. However, sine inverse of 0 is 0, so this guy's going to be 0. So on step 3, when we take our limit, we're only taking the limit of that. Limit k goes to 2 from the left of sine inverse of k over 2. Okay, whether k goes to 2 from the left or the right, it doesn't really matter. You're still going to get 2 over 2, which is 1. So you're going to get sine inverse of 1, and that is pi over 2. Determine if the integral is improper. If so, rewrite it as the limit of a proper integral. So let's look at these. Let's graph our interval 0 to 3. And then we look at this guy and we say, all right, does this have any problems on that interval? There's no problem at 0, because you get 1 over negative 3. That's fine. But up here at 3, there's a problem, because we get 1 over 3 minus 3 is 0. So the problem is at 3. So we're going to put k close to 3, and we're going to integrate from 0 to k, 1 over x minus 3 dx. And then the limit in front, we're going to push k to 3 from the left, because k is less than 3. Limit as k goes to 3 from the left. Okay, this one, 0 to pi over 4. Now, secant is 1 over cosine. So think of it as, think of this as the integral from 0 to pi over 4 of 1 over cos x dx, because what we're worried about is 0 in the denominator. Cosine of 0 is 1, so we have no problem there. Cosine of pi over 4 is 1 over root 2, so we have no problem there. And there's no problems in between either. So this guy's not improper. So I'm just going to write NP for not improper. I guess it would be NI. Okay, let's look at the next one. Here's 0, here's 1. We know ln of 1 is 0, but that's not a problem, because 0 in a numerator is fine. It's 0 on a denominator that's a problem. However, we do know that natural log has a problem at 0. So I'm going to put k here, and I'm going to integrate from k to 1 x ln x dx, and then I'm going to push k towards 0 from the right. So the limit as k goes to 0 from the right. And then that's it.